So we have three ways that we can hook up these transistors and amplifiers. Right now we're looking at what we call the common emitter connection. And what would be the other two? Common base and common collector. Now, first thing we have to understand about an amplifier. So what's the function? What type of gain? So amplifiers give us gain, right? You understand? And what kind of gain are we looking for? We're looking for power gain, right? So what does that mean? That means we need to get more power out than we do what? Than we put in. And then this is something we need to look at. What we talked about is going through stages of amplification. Now remember, amplification we give as multipliers, right? So if we say it has a gain of 10, that means we get 10 times out more than we put in. So I can figure, and of course I'm not talking, that would be current gain or power gain or voltage gain, but primarily we got two gains we basically can get out of an amplifier. We can get voltage gain or we can get current gain. Y'all understand that? But we're looking for power, but we know power we calculate by V times I or I square R, but V times I is the main formula that we're looking at. So what they're showing us here, if this guy gives us a gain of 10 and we feed that into a gain of another amplifier that has a gain of 10, what would be the total gain from input to output? Not 110, it's 100. So I say like I'm going to triple your salary. Right, so what we do on gains, when we go through stages of amplification, what we do with gains is we just do what? We multiply them together. We don't add them. Right, you understand? So if I said 3 times 5 is what? 15. So let's say I go through 3 gains. I said 3, I take 5 in, right, you understand, and I get a gain of 3. Then I take that gain and feed it into another amplifier that has a gain of 3. Well, okay, so I take 5 in, I get a gain of 3. What does that give me? 15. I take that 15 and put it in a gain of 3, and I get what? 45. So you don't add gains together. All you have to do is just multiply, just multiply them, right? So all in all, it's a gain of 3 and 3 would be a gain of what? Huh? Yeah, be a gain of 9, right? So if I knew the two gains, I'd say, okay, I'm putting 5 volts in. I got 2 amplifiers that's got a gain of 3. 3 times 3 is 9. Well, I can take my input and multiply it by 9, which would give me what? 45, right? Y'all understand? So gains multiply. So that's what we do is we start off with a very low gain, because most of the time when we have amplifiers, we go through stages. Because especially in audio, the more gain you get out of an amplifier, the noisier it is. And also we're dealing with resistances, or what we call impedances, between the amplifiers. And we'll look at that a little bit in this demonstration. We talked about bandwidth. Are you okay? So what is bandwidth? Well, it's actually a range. Well, that a media can reliably pass, right? You understand? And the main part is the half power point, which occurs at 70.7% of the voltage, right? So when the voltage drops down or rises up to 70.7%, then the power has increased or decreased by exactly 50%. Y'all understand that, right? Yes or no? Huh? Very important. And this occurs at what we call 3 dB, and we'll look at that. Well, we need to understand dB here in a minute. So what we're trying to do is, power is hard to measure, because when I measure power, I have to always measure 2 quantities, right? To measure voltage, I can do that with an oscilloscope or a meter. To measure current, I can do that with a meter. But to measure power, I've got to measure voltage and what? Current. So what we're trying to do is trying to see power relative to voltage. Now remember, voltage and power vary with the square, right? Y'all understand that concept, right? Y'all ought to. I teach that a lot. I think I'll put that question on the next test, but it says if I double the voltage to a circuit, what happens to the power? And see how many people in this class says it's going to double. It would actually quadruple, right? Because it varies with the square. Decibel unit, and the book doesn't do a real good job on it. What I'm going to do is I'm going to bring up I'm going to open up another PowerPoint that's solid white so I can draw on this. Now, why do you learn engineering notation? Well, why do you learn it? Why do they even, to do what? Not only smaller numbers, but large numbers. Y'all understand? So what it does, it gives us a method of dealing with very large and very small numbers. But once you learn it, and I say 100 milliamps, you know in your head what that is, right? You understand, because you learn these engineering notations, and we teach you that. So, you know, instead of me saying point, or, you know, if I've got 200 microamps, instead of me saying 0.0002, right? You understand? So what it does, it allows us to deal with very large and very small numbers, and it's a form of scientific notation. Now, scientific notation is when we take a number, and we multiply it times 10 raised to some power, right? So you don't use the y to the x key, you have to use the times 10 key, or times, so we use this key, which EEE, which stands for times 10 raised to some power, or I think some calculators call it the EXP key, which would be times 10 raised to some power, right? Everybody okay? Now, what's a logarithm? We have two types. We have what we call, we're going to deal with common logs. We're not going to deal with natural logs. Natural logs are really easy to understand. What is a logarithm? A common log. We call this a common log. That's what we're going to look at right now. A common log. Chase, you ought to know. You talk about it. So a scientific note, and of course engineering notation is a form of scientific notation where the exponents are always divisible by 3. So that's why we go, right, we go units, then we go -3, -6, right, -9. On the positive side, we go +3, we go time to the third. What is a log? So a scientific notation is a number multiplied by times 10 raised to some power. A log is this. It's times 10 raised to some power. And this is the log right there. It's the actual exponent. It's not the base. So on a common log, the base is always 10. So if I gave you a log of 10, what would that be equal to? What's that? No. What would that? No. It would be 10 raised to the 10th power. That is common law. And we can represent so logarithms are a method of representing very large and very small numbers with 1 digit or 2 digits, right? You understand? Very few digits, where scientific notation is a number times 10 raised to some power. A logarithm is the exponent of 10. Now, through time, I don't know how I got the name. So if I had a log of 2, that represents 100, right? You understand? If I had a log of 3, that would represent 1,000, right? You understand? If we have negative logs of 10, that's a negative number, right? You understand? By the way, over time, what they did is this became known as what we refer to as a bell. So you'd say, okay, you'd call this 3 bells. And that would tell you that would be 10. It's not spelled, it's with 1 L. That would be 10 raised to the 3rd power. So what is a decibel? Now what we do is you can represent any number with logarithms. So you can just make up a number. So what I'm going to do is bring up my calculator. So every scientific calculator has a log key. There it is right there. And you need to make sure it's set up for common logs, not natural logs. And right beside it usually is times 10 raised to some power. And this is what people try to use on engineering notation, but you don't use this on engineering notation. You use this key right here, right? You understand? So what I would do is I could make up any number. Oops. I could make up any number, right? And then I could come up here and hit the log key, and that would be the log of that number. That would be the bells of that number. So what I end up with is I end up with more numbers than I actually started off with, right? You understand? So what are we going to do? Well, we need to round this. Well, they came up with a method of rounding that we call decibels. So gains are usually given in dB. And we abbreviate that lowercase d, uppercase B. Stands for the decibel. And this is a method of using logarithms where you round. Because if I was going to use, what did I do with my calculator? If I was going to use this, it would be a waste of my time. Because the number I'm trying to replace is bigger than the number I started off with. So I would come up here and round it, right? Now, as soon as I round, I become less accurate, but you understand electronics and audio is approximations anyway, right? We approximate anything. So when we say 0.7 volts, that's approximate. When I say 100 ohm resistor, that's an approximate, right? You understand? Because every device we have in electronics has something called a tolerance. But we don't use tolerances when we do our calculations because we understand, of course it would be a lot of calculations, like resistors would have upper tolerances and lower tolerances. So it means if I wanted precision, I would calculate the upper tolerance and the lower tolerance, but that would still only tell me that my measurements are going to be somewhere in the center, right? You understand? Or somewhere between the two. So normally when we do calculations, so in this class, in DC, you actually measure your resistors because what you're trying to do is you're trying to prove that I is equal to V over R. You're trying to prove that R is equal to V over I. So what you do is, y'all remember those labs? What'd you do? You color-coded the resistors, you measured them, and what did you do in your calculations? I mean, your calculations, you used the measured values. And that way what you found out that Ohm's law was right. In this class, we don't use any measured values. We just do what? We just use the color-coded values because now we understand that our math is perfect, but our components are not. So that means when you start using logs, it would be a waste of my time to use this as the log. So what am I going to do is I'm going to round this. Now, the more we round it, the less accurate my number would be. Right? So this is the number that I started off with. And let's get rid of the fraction to avoid confusion. Okay. So I'm going to write that down. Oops, what was it? 1, 2. Yeah, somebody write that down. 1, 2, 5, 8, 9, 6, 5, 8. Now that's the number, right? You understand. But when I hit the log key, That's going to give me the bales that represent that number. Y'all understand? You can do it on your calculator. That would be nice too. Okay. So I'm going to hit this key. So that's a huge number. But if I raise 10 to that power, so I'm going to go right over here and raise 10 to that power, and I come back with the number I started off with. Right? But if I round this, so let's say 7.1. So I'm going to come up here and I'm going to enter 7.1. Oops, sorry. 7.1. And then I do this. Then I don't come up with exactly the same number. But it's close enough, right? Y'all understand what we're saying? Yes or no? Everybody okay? So what was the number I had? 1, 2, what?
5, 8, 9, 6, 5, 8.
Okay. So I'm gonna bring this again now. I'm gonna go here. And what I'm gonna do is, this is not a good number. Okay. But we got so then we used what? We used 7.1 for our bales. Well, what I'm going to do to aid in rounding, I'm going to convert this to something we call dB. Now, what we do on dB is we take the bales and we multiply it by 10. So 7.1 bales would be 71 dB. And that's why it's called a decibel. And then what we do is we round the number to some digits. This one wouldn't make any sense. Let me come up with another number. Okay, this is a good one. Okay. That's still not good. So I could round this to 14 dB. Right? You understand? Or I could round it, well, that only rounds one way. So I could round this to 18 dB. Right? You'll see what I'm doing in my head? Because when I multiply by 10, all I do is what? Just move the decimal point. Right? Now, what was my original number? My original number was 68. Or I could say 18.32 dB. Now, normally you see dB either rounded to 1 decimal point or 2. You'll never see it rounded. I've never seen it rounded to more than 2. So let's say we round this to 2. Okay, so I'm going to put 18.32 when it's in dB. So what I'm going to do is I'm going to multiply this by 10. Oops, lost my number. Of course, we don't have to do this. We can do this in our head. And then I'm going to round that to 2 digits, which would be 18.32 dB. 18.32. And then I'm going to get a log of that. Oops. I'm sorry. I screwed up. 18.32 dB. Now what would I do in my head to take it to the number? I would shift the decimal point to the right, you understand. I'm sorry, I'd shift it to the what? To the left. And I would come up here and I would use 1.832. .832. And then I'm going to raise 10 to that power. Supposed to be what? 68, and it came up to be what? Now, if I come up here and say 1.83, and then I go that, then it's gone to 67, but it's still okay, right? You understand? And then if I go to 1.8 and raise it, it's still okay. But the more you round, the worse your answer, but it's still a good approximation. So a lot of times you see when they give dB, they just round it to 1 decimal. I mean, they round it to no decimal. They just round it to 2 digits or 3 digits, depending on how many dB you have. Everybody okay? Understand that? So the way we calculate the gain, the power gain, is, so dB, now that's like using milli, so it's not actually a unit. It's not volts, it's not amps, it's like when we say milli or we say micro or we say those kilo, those are the same thing. But here we say 10 dB, right? You understand? Which are just like me be saying 100 milli. So this is not actually a unit. It's still a number. So dB, we do this, you might have to enter this backwards. It depends on what type of calculator you got. The formula is log 10 times AP. So this is telling us to do what? It's telling us to take the power gain, multiply it by 10, and then do what? Then take the log of the number, and that'll give us dB. Everybody understand that? So on my calculator, I want to get the power gain. What power gain do y'all want? That make a difference. A while ago it says we had a power gain of 100. Or it said we had a gain of 100. I didn't say whether it was power gain or not, but so I would come up here. If I got a power gain of 100, log 10, I'm sorry. Oh, this is not right. We need to do what? Okay, that's backwards. So I've said this wrong. So what we do is we take this, and then we take the what? Log, and then we multiply that times 10. So this is what we'd actually do. We take the log of AP, and then we'd multiply this times 10. Y'all see that? So dB would equal to the log of AP. And what's AP? Huh? What kind of gain? Power gain. And then we multiply our answer by 10. But this is the way the formula is given right here. Log 10 AP. Now remember, power varies with the square of the voltage. Y'all understand? Yes or no? So if I raise 10 to the first power, it comes up and gives me 10. If I raise 10 to the second power, it comes up and gives me what? 100. So that would be the same as 10 squared. Y'all understand that? So if I'm measuring voltage, then dB would be equal to the log 20 times AB. So 20, remember, if I move this over, that'd be like me taking 10 to the first and going 10 to the second, and that's going to square it, right? So it's going to square the voltage. So if I double the voltage, what happens to the power in the circuit? Huh? If I double the voltage to a circuit, what happens to the power? That's going to quadruple. Y'all understand? Yes or no? The example I use, because remember, so voltage and current, if resistance is constant, voltage and current are directly proportional. So if I come over here and go from 10 amps, okay, so if I'm calculating power and I use 10 amps at 10 volts, that's going to give me 100 watts. If I double my voltage, that means my voltage goes to 20, right? You understand? Which is going to cause my current to go to 20, which is going to cause my watts to go up by 400. if I raise my voltage up to 7.07 volts, 7.07, my current's going to go to 7.07, and my power would go up to what? If it drops, yeah, 50 watts. Y'all understand 7.07 is a round. It's actually the reciprocal of square root of 2. Square root of 2 is 1.41414144. So if you was to do that for 0.707, it'd be perfect. So we can't measure that fraction anyway, so 70.7% would be fine. So if I had a voltage gain of 10, what would be my power gain? So I'd take the dB would equal to what would be my equivalent power gain. So what I'm going to do, I'm going to take AV, and I'm going to take the log of that, and I'm going to multiply that by what? 20. That makes sense? So if I knew the current gain, this formula would be the same because it varies with the square of the current or it varies with the square of voltage. So if I measured the current gain, I would do the same thing, but it would be AI log times 20, right? You understand why the 20? Because what are we doing? We're basically squaring the voltage, right? Because 20 dB is the same as a square. So what would I do if I knew the voltage gain? If I knew I had a certain amount of dB, let's say I have 21.1 dB, what would be the actual power gain? So what I would do, I would raise 10 to the 2.11 power. You understand? What would that come up and give me? Well, this is what's nice about dB, because most people understand powers of tens. So you can get a pretty good approximation in your head, right? So I know this is going to be over 100, but it's going to be less than 1,000. Now, it's not really accurate, but it knows, I know a range where it's going to fall into. So what, huh? Yeah, that's what it was. Everybody okay? So what we're doing here, if I can measure the voltage gain, this is supposed to give me the same answer as if I did the power gain for the same circuit. Y'all understand that? Now let's look at this 3 dB thing, minus 3 dB. Let's see. Sometimes I have problems with this, but I'll try to not make any mistakes. So I got a minus 3 dB. And we're measuring, yeah, well, if it's a minus, it's a loss. We still called it a gain for some reason, but it's actually a loss. It's actually an attenuation, which means I've lost it. So anytime you see a minus dB, you know you're getting less out than you put in. Anytime you see a plus dB, you know you're getting more out than you're getting, right? So it's just like when we represent milli, we multiply the number times 10 to the minus third. So as soon as I see minus 3, I know that that number is less than 1. Right? You understand? And anytime I multiply by a fraction, I come up and get less than I want. So I want to get the power of 10. So what would I do right here? Let's do it. Let's divide it by 20 to get the voltage. So minus 3 dB divided by 20, what do I get? I close out my calculator. So 3 divided by 20 equals that. Okay, I'm going to change the sign of that, and then I'm going to raise 10 to that power. 0.707. If I did minus 3 dB, so I'm going to say 3 dB, I'm going to say 3, I'm going to divide that by 10, because here we're dealing with power. Okay. And then I'm going to raise 10 to that power. I'm going to change the sign, and I'm going to raise 10 to that power. Should come up and give me 50%. Let's see that. So it's minus 3 dB would be a 50% drop in power. But now we got to say, okay, what would it be if I was measuring voltage? So what I'm going to take that 3 dB, I'm going to change the sign, and I'm going to voltage, so I'm going to divide it by 20. Okay. Now remember, we're doing a lot of rounding. And then I'm going to raise 10 to that power. This is where the 70.7% comes from. So a 70.7% drop in voltage is the same as a what? 50% drop in power. Y'all understand? So that's when we say, when we measure our bandwidth, you'll see people say it's minus 3 dB, because what are they measuring? Well, they could be measuring power, but odds are they're measuring what? They're measuring volts. So that means if this right here was 10 volts, when this came up to 7.07 volts, or this dropped down to 7.07 volts, what just happened to the power? Dropped by what? It dropped by 50%. Y'all understand that? So a 50% drop in power, we call this 3 dB. So they say a 3 dB drop would be 50, if your voltage drop, if your power dropped by 50%, it would be 3 dB. Or if your voltage dropped by 50%, it's going to, 70.7%, it's going to be 3 dB. Y'all understand? Yes or no? So when we talk about bandwidth, we have two frequencies. We call this guy here F1, we call this guy here F2. This is the way we measure it. Bandwidth would be equal to F2, it would always be equal to F2 minus F1. That would be your bandwidth. Now, of course, this is the way we do what? This is the way we measure. Of course, what do we need to know how to do? And we're not going to teach that in this class before we measure something. What do we need to know before we make measurements? What we're looking for. So that means there's some way we can calculate the bandwidth before we do what? Before we measure. It's just like when we measure VB. If I don't know what VB is supposed to be, right, you understand, then making measurements are nothing. Not unless it's operating perfect. If you got an amplifier that's operating perfect, and you go through and measure those biases, then they mean something. If you got an amplifier that's not working and you don't know what they're supposed to be, and you go through and measure those biases, it don't mean anything, right? Don't understand. That'd be like calculating your miles per gallon. You don't know how much gas you had to start off with. So normally, what do? Normally, of course, cars do it for you now. Yeah, you top it off, and then you run it. You record. And then you go back and do what? Take your mileage and top it off again and see how many miles you went on that many miles a gallon. That's what we used to do. Of course, now most cars do what? They calculate it for you, yeah. But since they got them computers in there now. So dB, what is dB? Deals with common logs. And what it is a dB? So we call this little guy up here, what's it called? We call it a bell. All right, you understand. And what is a decibel? We take the bells and multiply it by 10. If we're dealing with power, we multiply it by 20 if we're dealing with what? Oh. So we do gains, we do losses. I can show y'all all kind of amplifiers and stuff like that where they talk about dB. You go out and buy a new stereo and you look at the specs. A lot of specs going to be in dB. You know, they talk about channel separation. You know, how bad does your left channel migrate into your right channel? That's all kind of stuff. Sometimes real high dBs are real nice. Sometimes real low dBs are nice too, right? You understand? So it all depends on what you want. The ear hears in decibels. So before we can hear a doubling in voltage, we have to go up a decibel. So your ears are in powers of tens. Normal ears, some ears are not. So your ears have a bandwidth, right? Extremely low frequencies we can't watch. We can't hear. Extremely high frequencies we can't hear. And then it starts off, comes up in an angle, then we can hear it real good, and then it'll start driving down. I'm looking for my speaker. Normally we hook a speaker up to the sky right here to let you see what the bandwidth of your hearing is. Now, next thing we need to look at in this PowerPoint is now this guy here does a very poor job on this. What we do is when we look at the types, so we got three types. We got common emitter, common base, and common collector. The next amplifier we'll look at is common collector. We won't get into the common base very much because it's very not used often at all. The common emitters and common collectors are used all over the place. But what we do when we talk about common, it has nothing to do with the DC common. It's the signal common that we're looking at. Y'all understand that? Because that gives people a lot of problems. They want to look at that common. So when I have here, and we're going to do signal flow, we're not going to do current flow. So I've got a common emitter. Now what a common emitter, how we identify these is we look and see what we input on and what we output on. And then the other lead has to be common. So on this guy right here, where's our input at? What lead of the transistors that on? We got three leads. We have emitter, base, collector. Where's our input? Which lead does our input go to? Huh? Guys, this... Okay, so the input's on the base. Where did I take my output off of? Okay, so my output's on the collector. So this is a common emitter amplifier. So what you do is you look at the amplifier and say, okay, where's my input at? Where's my output at? And the one that you don't say is what is actually common. So the signal comes in here and flies through here. It goes that way, it goes that way. What does the signal do up here? What does an AC signal see a DC source as? Huh? It sees it as a piece of wire. So you can't say it sees it at ground, it sees it as a piece of wire. An AC signal will fly through a DC source like it's not even there. A DC signal will fly through an AC source just like it's not even there. Okay. I would show y'all that, but we'd short our, let's see, let's see if we can do this with electronic workbench. It hadn't been working too good for me over there. Oh, if your input capacitor shorts, your input signal pops to 0, which is pretty interesting. Come on, come on. What do you think about Watch the Living Dead? Did y'all watch the Walking Dead this week? So that it was, oh yeah, I started it. Okay. So what I'm gonna do is I'm gonna come over here and bring in an AC source. Hopefully it don't crash on me. Now if we had a fuse in here, this would blow. So I'm gonna hook it up to a DC source. First of all, I don't know if it'll let us get by with it, we'll see. So I'm gonna take my meter and put it across there. Let me use these right here. You might tell me I got problems in my circuit because I don't have that thing grounded, but we'll see. Okay, got it set up to measure AC. Okay. And we'll turn it on. It's measuring what? Okay. What I'm going to do is I'm going to come in here and connect this guy right here to ground. I'm going to turn it on. What does it say? Well, let me do it. Does I have a what? So it said I have a short circuit. What we'll do is let's bring a big old resistor right here, so we don't short it. We'll put it right there, and we'll make it like 1 meg. Okay. I'm gonna disconnect the ground from here. Okay, I'm gonna turn it on. And the meter's got resistance. Let's change the meter resistance up to. This is one of those situations where you think your meter don't affect the circuit, but it does, right? You understand, especially when you're dealing with high resistance circuits. So what's dropping the voltage? Of course, this is dropping the voltage because now we have current flow through the meter. What I'm going to do now is I'm going to turn this off and connect the battery. Okay, turn it back on. So what does that mean? If I looked at the voltage drop across this resistor, it's dropping the entire voltage. Y'all understand that? So an AC source sees a DC voltage, a DC power supply as a what? As a piece of wire. And we can come up here and swap these around. So let's so what would you think an AC voltage source would see a DC? What would you think an AC would see a DC? Yeah. Huh? Okay, so let's look. So I'm gonna put my meter over here. Okay, I'm gonna get the common. I'm gonna connect this up. We're gonna make a circuit through the meter. I'm gonna turn it on. And it measures, we need to change the size of this resistor. Let me drop it back down. My meter's dropping all my voltage. Oh, I got it on AC too. Duh. See, I did the same thing y'all did. Okay, so it's measuring what? Well, yeah, because okay. Now what I'm going to do is turn it off. And I'm going to hook up my common over here. I'm going to put a common right here. My meter's measuring across the, now the AC is there. I mean, it's there. And what does it go to? It goes to 0, right? I mean, it's not real good. Yeah, just give it time. So what does a DC source see an AC source at? A piece of wire. What does an AC source see a DC source at? A piece of wire. Y'all understand that? So what that means is if I come over here and I'm drawing my current flow, this guy right here is going to see my DC source as a piece of wire. So my DC source comes over here, is connected like this, right? I'm using negative common. So it's going to see that just like this. Huh? And then, of course, it's going to go this way, because that is common. And then my DC signal is going to flow that way. Right? You understand? Okay. So my AC, my input is actually like this. So I come in through my capacitor. I go through R1. I go through R2. Then I go through my transistor and then RE. But RE is seen as times beta. That's the input circuit right there. That's exactly what your input is. So that means I can calculate that input resistance right there. Y'all understand that? Now watch what I'm going to do now. Now what we can do here is we can bypass it. And what does that do if we bypass it like that? So this is called, these two guys right here are called what? They're called coupling capacitors. And what's this guy right here called? It's called a bypass capacitor. So what happens now with the signal? The signal is going to come through. It's still going to go this way. It's still going to go this way. But now the signal is going to bypass RE. And that's why it's called a what? A bypass capacitor. So before, our calculated gain was equal to RC over, or RL over RE. Now your calculated gain is going to be equal to ROUT, over RE prime. And RE prime is little, right? You understand that? So the gain goes up astronomical. I think last time, just by jumping it out, we went from a gain to a 10 to over a gain of 100. Just by doing what? Jump it, bypass. Okay. So watch what I'm going to do. So what kind of gains can we get out of this guy? We can get a voltage gain, right? We can get a current gain, which means we can definitely get a what? Yeah, a power gain. And this is what we'll find out on all these. We can get a power gain. So if I don't get a current gain, but I get a voltage gain, we still get a power gain. Right? You understand? If I don't get a voltage gain, but I get a current gain, I still get a power gain. Right? You understand that? This has a low input resistance, especially when it's bypassed. And it has a high output. Because we got to put that big old guy right there, right? And of course, the input signals and the output signals are 180 degrees out of phase. Which most of the time is no problem. It's just like a saturated switch. The input's going high, the output goes low, right? You understand? So even on a saturated switch, it's 180 degrees out of phase. So if I want to close the switch, I put a voltage on the base or current through the base, right? You understand? Which causes we take our output across the transistor drops to zero. And we need to talk about something else. So what I'm going to do is I'm going to take this resistor out right here. And I'm never going to bypass this guy. Never. So we never bypass this amplifier. And what I'm going to do is I'm going to take my output, instead of taking it right there, I'm going to take it out here. Hang it. And we'll see how we do that. This guy here is actually a lot easier to calculate.
Okay.
I don't know what I've done to my marker, but anyway. Where do I change the size at? Let's see. Great size. Oh, I see. Still up there. Yeah. So what we're going to do is we're going to take our output right here. So what type of amplifier is this? I'm inputting on the what? I'm outputting on the emitter. So what type of amplifier is this? Common collector. So your input comes in, still sees basically the same thing. This is a common collector. Comes in, goes up, slides to this guy here like it's not there, right? Goes to this guy, and we'll always have RE right here. So this guy here has a fair, and these resistors right here, by the way, are going to be equal. So if this is a 10K, this right here is going to be like a 10K. We'll talk about why later on. Normally, if we're going to operate this Class A. Now, how much voltage gain am I going to get out of this guy? Now we can put almost any voltage we want. So let's say I put 10 volts right there. What would the voltage be right there? How much does this junction right here drop? 0.7. So what would the big voltage be right there? It'd be 9.3. Right? Don't understand. So what we find out, this is called a common collector. Number one, the voltage gain, according to this, the voltage gain would always be close to 1. Now what we're going to do is we're going to bias it on. So right now I'd have, let's say I'm going to put 10 volts up here, right? You understand. Then we would vary these a little bit. So if these are 10 volts, what would this base be right here? If I put 10 volts right there, that's a 10K and the 10K. What would the base be at? What? If this is 10 volts, okay, these are two resistors that are the exact same size. So that means they got to drop the same voltage. I got 10 volts to work with. Kirchhoff's voltage law says the sums of the voltages have to be equal. So what would that voltage be right there? Come on, guys. This is easy. It's going to be 5 volts. Okay? Y'all understand? Okay? What would I have right here? I'd have 4.5 4.3. Okay, the transistor, is it on or off? Is it on or active? Is it active? Well, right here I have 10. Right here I have 4.3. Voltage collector to emitter would be equal to what? 5.7 volts. Is it active? Saturate? It's active. So what's going to happen if I bring in 1 volt peak to peak? What am I going to get out? Seven-tenths of a volt's gone. The transistor's turned on. The bias turned the transistor on. You understand? So what I would get is I would get almost 1 volt peak to peak out. I wouldn't get quite because of that little RE prime right there. That little RE prime is going to drop just a little bit of the voltage right there. So our output gain is going to be slightly less than 1. Well, a lot of people say 1 because it's going to be like 0.99 something. So I don't get any current gain out of this guy. But man, it's easy to calculate. I mean, good gracious. Because these two resistors over here are probably going to be pretty close to the what? Same size to set this up to be what we call class A. Normally this resistor down here might be just a slight bigger because we would like this right here to be sitting at exactly half of VCC. If we make them the same size, it's going to be 7/10 of a volt less than half, right? You understand that? So we can't get voltage gain out of this puppy. But what we're going to do is this resistor over here is going to be really small. And this is where you'll connect your speaker. Normally on this guy, we'll come up here and actually put your speaker coil right there. It's actually in the emitter, so we don't have to output it. We'll look at it later on. And these guys here, standard home speakers are 8 ohm speakers. So my input is feeding in through all these resistors, right? You understand? My output is going to be across a small resistor. So what type of gain are we going to get out of this guy? Am I going to get voltage gain out of it? Yes or no? No, because we're taking the output off the emitter. The emitter is following. Some people call this the emitter follower, by the way. This is another name for this, because the emitter is following the base. So whatever's on the base is going to be what? On the emitter. It's just going to be slightly less because of that dynamic resistance of the base emitter junction. But we're talking about like 0.95, 0.99, something like that. So I can't get any voltage gain out of this. But here we're inputting, if this is 10K and this is 10K, this would be times beta, which would be 10K. So my input is going to be looking at what? About 3.3K. My output is looking at 100 ohms. My input is going to be inputting on this. My output is going to be on that. So the current out is going to be a lot more than the what? Current in. So the big advantage of a common collector is we get a lot of current gain out of it. No voltage gain, but a lot of current gain. What determines how loud a speaker is? It works off magnetics. What determines the strength of a magnetic field? What determines the strength of a magnetic field? On an electromagnet, what determines the strength of the magnetic field? Yeah, I'm looking for V or I. What determines the strength of a magnetic field? Because we're talking about a gain here. What determines the strength of a magnetic field? V or I? I. Has nothing to do with V. Of course, you can't have V without it. You can't have I without V. So what we get out of this guy is we get tons of current gain. So the outputs on your stereos are going to be common collectors. The rest of yours will probably be common emitters or some form of that. So we get all our voltage gain with the common emitters, right? Does that make sense? And then when it gets time to run our low impedance loads, our low resistance loads, we're going to use something that has the low resistance output. And that's one more thing I'll show you. I've got two more things. We'll go get more into more detail of this later. I need to let me bring up my PowerPoint that I use in normally when we start dealing with AC signals, most people don't use the term resistance, they use the term impedance. If you add AC, you'll understand that. If you don't, but usually the term impedance is a term that we use for opposition in an AC circuit. Because opposition, we have reactance and resistance in there, right? Well, what we're trying to do is set up something we called, let me find it. So what I have here is, y'all do the calculations for me. And Chase, you don't need to answer this, and you should know this. If you don't, okay. So what I'm going to do is I'm going to come over here on this circuit right here. And you got to understand, when we start talking about power sources, it depends on what type of power source you have. Everything has resistance. And if you push current through resistance, you get what type of drop? Huh? Well, you get what type of drop? Voltage drop. Okay. So that means Alabama Power is very concerned. They call it line loss. So even conductors give you line loss, right? And what determines the resistance of a conductor? What it's made of? The size, right? Or we call it the gauge, and the distance, and then the temperature. Power sources have resistance. So it means if you try to get current out of a power source, the voltage output will do what? Drop. If you don't believe me, go out there and don't crank your car up and put a meter across your battery and turn on your lights. What will the voltage do across your car battery? They'll drop. Now remember, your alternator, we have what we call a regulated power supply. We understand that now, right? So your alternator has a regulator on it. So what that means is if the output of the alternator drops down, they put more power into it, right? They make more power available. Signal sources are not regulated. So here we're talking about amplifiers. We're not talking about power anymore. We're talking about signals, right? You understand? Every signal source has an opposition. So it means if I try to pull too much current out of it, I'm going to get a voltage drop. So I don't get as much out of the signal source. So what I'm going to do is I'm going to come over here. We're using a 100 ohm resistor right here to represent the internal resistance of the signal source itself. And I'm going to load this down. I'm going to load it down with a 10 ohm. I'm going to load it down with a 100 ohm. And I'm going to load it down with a 1000 ohm. Which one do you think will provide the most power to the load? So I'm going to make my load equal to 10 ohms. I'm going to make my load equal to 100 ohms. I'm going to make my load equal to 1000 ohms. Which one of those do you think will give me the most power to the load? Chase can't answer this because he already knows. 1000. What do you think, Drew? What do you think, Drew? Which one? To the load. 10, 100, or 1000? What do you think, Dwayne? 10? So what we're going to do is we're going to come out here and we're going to connect it. First thing we're going to do is we're going to put the 10 ohm resistor in there. And we're going to calculate this. We'll probably use the voltage divider formulas because it's so much easier and we can combine everything with one swoop. So what I need to do is calculate power. So what I'm going to do is I'm going to say V across my resistor, across my 10 ohm, right now we'll call it R1, would equal the 10 times 100, divided by 110, excuse me. We're going to do this in one formula because y'all can do it all with one formula. So we're going to use two formulas here to do it real fast. We're going to use the power formula. So one of our power formulas is V squared over R. Right? Y'all know that one?
Okay.
So what I'm going to do up here is I'm going to go directly, I'm going to use two formulas in one to calculate them real fast. So I'm going to say the power across R1 would be equal to, you could do that, would be equal to what? It's going to be equal to 10 ohms divided by 110 ohms, right? Times, what are we applying to it? 10. And then what am I going to do? I'm going to go, as soon as I hit that equals, I'm going to do what? Square. And then I'm going to divide it by 10. And this is going to give me my power. So what we're doing is we're combining the voltage divider formula with the power formula. And that way we can do it all with one equation, right? Anybody got it? So I'd come up here, I'd say 10, this is the one I want the voltage drop across, divided by 110, which is RT, right? I'm going to hit equals, and then I'm going to multiply that times 10, and then I'm going to square it, and then I'm going to divide that by 10. So I got 82.6 milliwatts. Is that what y'all got? We okay? $82 milliwatts. That's what I came up with. Okay, but I rounded. Are we okay? Okay. So what I'm going to do now is slap the watt. I'm going to slap the 100 in. Okay, y'all calculate that. So now we're going to do 100 divided by 200, right? You understand? Multiply that by 10. That's going to give me 5. Right? Square it and divide it by. What we got? No, what? 250 milliwatts, I think. Yeah, the math is up here. So 250 milliwatts. On the line. Okay. 250 milliwatts. Okay. So it looks like if you said 10, you were wrong, right? Okay. So what we're going to do now is slap the 1,000 in there. So we're going to have 1,000 divided by 1,100. We got it? I know what it is already. Does it come up and give us 82 again? Oh my goodness. So when did we get the maximum power transfer to the load? When the impedance of the load matches the impedance of the source. Y'all understand that? We refer to this as impedance matching. In communication channels, it's imperative that we have impedance matching in the system. That's why on your TV, why don't they just run 2 wires into your TV? Why do they use that coax cable on your cable? Because it is 50, it has an impedance of 50 ohms. The amplifiers in the cable system has an output impedance of 50 ohms. Your TV has an input impedance of 50 ohms. Now this is not resistance, this is what? An impedance, which is AC, right? You understand that. If all the impedance matches in a communication system, then you get maximum power transfer from the transmitter to the what? To the receiver. So that's why when you hook up network, you have to use that standard twisted pair cable. You just can't run wires. It's a 100 ohm cable. It's a 100 ohm cable at 10 megahertz. Cat 5 cable, 100 ohm impedance. You can't measure it with a resistance. If you measure it with an ohm meter puts out DC. So the capacitance of the cable you can't measure, right? And the inductance of the cable you can't measure. So that means when you wire up networking, by George, you better use the right conductor, right? You just can't, you got to use the right cable, because if you don't use the right cable, you screw up your impedance matching. If you don't have impedance matching, then you don't get maximum power transfer to your load. And that's what we're trying to get to, right? In communication channels, we don't let this be arbitrary. It is set. So instead of it being arbitrary, we set the impedance of the cable. We set the impedance of the amplifiers. I can go over here and open up the ABB robot, and you'll see a dang resistor in there. And why they got a certain size resistor in there? To set the impedance of the channel, right? You understand that? So when you get into communication systems, we're worried about impedance. And amplifier impedance, what we're doing is we don't want a low output impedance amplifier to feed a high input impedance load. Doesn't make any difference, right? You understand? So to get maximum power transfer, my speakers are very low impedance because we're trying to get a lot of current out there, right? You understand? So I want the output impedance of my amplifier to be what? High or low? So I don't want a high impedance amplifier to feed a low impedance load, right? You understand? So the common emitter output impedance is high. The common collector output impedance is what? Low. So that's why we use common collectors to drive speakers or drive big power loads. Anything that needs a lot of current, we're going to use a common collector. Anything that needs a lot of voltage, we're going to use a common emitter. That makes sense? So a common collector has a high input impedance and a low output impedance. So I can connect a common collector input to a common emitter amplifier. Because a common emitter amplifier has a high output impedance, a common collector has a high input impedance, right? Does that make sense? I can connect the output of a common emitter to another common emitter. But I can't connect the output of a common emitter to a low impedance load, like speakers or like relays or stuff like that, right? You understand that? Because they need a lot of what? Current. That makes sense. Because what are we shooting for? Impedance, what we call the impedance matching. So that's a good test question. So when the impedance matches in a communication system, what do you get? You get maximum power transfer from the transmitter to the receiver. So you take your car antenna off. It's got a piece of coax antenna. It's got a coax wire running from the antenna down to the back of that radio. Have you ever pulled the radio out before? Well, what if you just hook just two wires up to your antenna? You just screwed up your what? Impedance matching. The story I tell, I know Chase has heard it before, is my father-in-law was pulling a not a moving van, but it was a U-Haul through his backyard, and he broke his TV cable. And he got him a ladder and went out there and just twisted the wires together. And then he complained about his picture being there. Because as soon as he twisted those wires together, he screwed up what? The impedance of his cable. Sure did. Had black tie. Looked pretty good. And also communication cables. We don't want to put these things in knots. I mean, we don't, the bend radius is really, really critical on these cables, because if you get them too close together, you're screwing up the what? The impedance of the cable. You don't tie them in knots. You don't, when you roll them up, you don't pinch them. You roll them in nice loose loops, because, what's that? No, they never have a tie. Normally what we do is we loop it, not because of that. We loop it so we can fix it when it breaks. I mean, you want to hear some cussing, you listen to some people that comes out and try to fix cables where the technician ran exactly what they needed. NEC requires at least 6 inches from the edge of the box, not the back of the box, from the edge of the box. So when you hook up your plugs, you got to have at least what? 6 inches from the wall where it exits the box to where your wires are. Now why? Because of what? Yeah, if they run exactly what they need, we repair those things all the time. Especially a lot of people on those new plugs, they use those compression, those slip plugs, instead of using the screws. I hate those things with a passion. They use those little compression where you slide them into the back of the plug. And how do you get them off? You cut them off, right? You understand? Well, as soon as you cut them off, you've lost maybe over about almost an inch of your wire. And you're going to replace plugs in your house. They go bad, especially plugs that you use a lot. Plugs are not supposed to get hot, right? And receptacles and wires and plugs are not, the cords are not supposed to just fall out of them either. So if you got a plug that stuff won't stay plugged into, what do you need to do? You need to change it. Go down to Lowe's and buy you one, but less than $1. You buy. I usually buy them in the tin groups. And keep them around the house. Change them out. They're not hard to change out, but I don't use those. I bend them and wrap it around. Power transfer between the transmitter and source and the receiver in the circuit is maximum when the impedances in the circuits do what? Every signal transmitter has some impedance. So every signal transfer has got some impedance. So that means if you try to load it, it's going to drop down. These are not very good signals of common emitter and common collector. And of course, common base is covered in your book, and it's covered pretty good. This is what I wanted to talk about right here. And this is not good either. Is the classes of amplifiers. Now there's more than this, but these are the, we have switching amplifiers, which I think falls in the class D and F category. You can research those and look at some of those, but these are just your regular old analog amplifiers that's been around for years. And what we're doing is we're looking at the relationship. I think I left the thing recorded, by the way, during the break. I'll expect cut out. We're looking at the relationship between the input and the output. And we'll look at three classes: Class A, Class B, Class AB, and then Class C. We talked about, oh wow, loading the signal, output impedance, and this is some of the things they're talking about in the chapter. So this would be output of a common collector, right? Feeding into a common emitter for some reason. So I don't know where it's at, guys. I can't find it, I'll just draw them. I tried to set some of them up, but I didn't have time. So we have what we call a Class A amplifier. A Class A amplifier amplifies 100, we call it 360 degrees, amplifies 360 degrees of the input signal. So what that means, if I bring a regular sine wave signal in this, so normally what we use is we use this guy right here as the symbol for an amplifier. In digital it's a buffer, but this is not digital. And what we mean is if I come over here and put this signal in on the input, then what I get on the output is I get the same signal, but it's going to be what? It's going to be bigger. Something's going to be bigger. Either current's going to be bigger, or the voltage is going to be bigger, or both of them's going to be bigger. So we get more out than we get in. Now the common emitter is still called a Class A amplifier, even though the input and the output are 180 degrees out of phase. So if this was a common emitter, if this was my input and this is what I got, this would still be called a Class A amplifier. Now, problem with a Class A amplifier is that it's got to be biased on. So when I come up here and do this, and I do a common emitter, and we don't need to bypass it right now. Oh yeah, we can bypass it. Since it's on, we got DC voltages out here, so we have to have all these capacitors. But here comes in my ACC. So to bias it on, to bias this thing and make it work, I've got to put a voltage right here. Or let's just say 2 volts. Now, is that the input signal causing that 2 volts there? Yes or no? No, it's that battery up there. Right? You understand. Which would set this down here. Well, how did that voltage get there? Well, that voltage get there because this amplifier is sitting there conducting current all the time. So there's current flow through those 2 resistors all the time. Even if I don't have an input signal coming in, this guy here consumes power. This guy here, we got current flow through here because we have to bias this thing on, right? You understand? So if I've got 20 volts over here, I have to put those resistors, and I'm trying to put that at 10 volts right there, without even an input signal on there. So this is not current gain. This is the amplifier itself requiring current to even work. Y'all understand that? Now when I bring a signal into it, now we change the current flow. But we have to buy, a Class A amplifier has to be biased on, even when you don't even have a signal coming into it. So that means you can go out there and rip the antenna off your dang radio, and you can put an ammeter and turn that radio on, and you can put an ammeter in that positive lead, and by George, it's going to sit there and pull current, even if your antenna's not even hooked up. You can disconnect the speakers, and you can power your radio up and put an ammeter on there, and it's going to pull what? It's going to pull current. So these guys here are very inefficient. Their rule of thumb is 25%. But they nice. They what but I don't have to do anything special because the output is a replication of the watt of the input. 25% efficient, Class A. So, man, if I want 100 watts out of this thing, that's going to be very, very cost inefficient, right? So that means it'd take 100 watts of power to get 25 watts out. So what they decided to do, I said, okay. And that's what I need to do is find my What if I came over here and I chose two resistors, same circuit, instead of trying to put that right there at 2 volts, let's say I biased so I had 7/10 of a volt right there. Now, of course, with no signal on the input, I still have this current flow right here. I need to do this in another color. I still have this current flow right there set in 7/10 of a volt, right? But it's very little now. Okay. So how much current would I have? If I put that at exactly 7/10 of a volt, how much would I have on my emitter? If that's at 0.7 volts, what would be my voltage right here? What'd you say with 0? How much current flow do I have over on the power side? How much current flow do I have? If this resistor right here is dropping 0 volts, how much current flows through it? 0. So that means my power side is right now is consuming no power at all without an input signal. So I bring an input signal on. So what happens when this goes up, the output would cut on, right? So right now this right here would be sitting at whatever voltage this is up here. So it dropped down, and then when it came up and went negative, it would cut off. So my output would look like this. So it kind of looks like a halfway rectifier. If I put AC in, if I put audio in there, it would just clip off the tops. But this guy here is a lot more efficient because it is not biased on, it's biased off. The signal turns it on. It makes sense. The signal turns it on. But I couldn't listen to my favorite music getting this garbage out right there because you lose 1/2 of your thing. But this is what we call Class B. And this guy here is about 75% efficient. Are we okay? Everybody okay so far? So what would you think an AB amplifier would be? What do you think a Class AB amplifier would be? A combination of both. So this is what we got. This is what your car stereo is. It has AB amplifiers in it. So what I'm going to do is I'm going to come up here. Now we're going to have to modify this a little bit. And we'll talk about it later on, but we're just going to look at the amplifier right now. So what I'm going to do up here, I'm going to put a NP in, and I'm going to connect this up to a plus VCC. I'm going to take this emitter, I'm going to connect it to this guy, I'm going to put a PNP down here, and I'm going to connect this to a minus VCC. And right now we're going to connect the bases together. And my output, I'm going to take right here. We don't have to put a coupling capacitor out because this sucker here puts AC out. This puts AC. It don't put AC. It don't put DC. It won't put AC superimposed on DC. It puts AC out. So I come over here. This goes positive. So right here I put no signal in. The output would be 0. All right, you understand that? And we're going to do a little bit about this. This would be a common collector because we're outputting on the emitters. But we're through with our current gain, right? You understand? We're through with our voltage gain. And now I would come out here and I put my car speaker right there. Don't have to put a coupling capacitor because it's going to output what? AC. Come over here and do this. This would cause the top one to turn on, which would cause my output to do this. Then it drops down to 0. They both cut off. then my input does this, my output's going to do this. So this is a B, this is a B, but my output looks like a what? Looks like an A. Now it's not. We're going to have what we call crossover distortion. When we get into these, we'll show you how to get rid of that. So what happens, it takes about 7/10 of a volt to turn them on. So really, if we didn't do anything right now, this is actually what we would get out. Right there between the negative and positive, we'd get a little flat spot. And why? Because it takes 7/10 of a volt to turn it on, right? You understand? And we'll tell you how to get rid of that crossover distortion later on with just a little bit of bias. And this would be what we call a class AB. It's two B's operating look like a class A. So if I go out and look at the output of my speakers out there, it's going to be AC. So your speakers, we can't put AC, we can't put DC across the speakers. Anybody know why? Why? Because X of L is equal to 2 pi, it's equal to what? 2 pi FL. What does DC, what frequency does DC have? Huh? Okay. So that means my impedance would be nothing but so if I put DC on the speaker, what my big DC up here, all it would see would be the R of the wire. That's all it would see. So we don't put DC on speakers. It'll burn them up. Because you measure those, an 8 ohm speaker is going to measure less than 8 ohms. Why is an 8 ohm speaker going to measure less than 8 ohms? If you had AC, why is an 8 ohm speaker going to measure less than 8 ohms? Because it's X of L. It's impedance. It's not a resistance, it's impedance. Car speakers are set at 1,000 hertz. So the impedance of a car speaker is what you get at 1,000 hertz. So you'll measure less than that, probably around 5 ohms. Look, 8 ohm speaker will probably measure around 5 ohms DC. That's why you look at those big old bass speakers, they got really heavy wire on there because they handle a lot of current because they don't have much X of L at 30 hertz, right? But your outputs are going to look like this. You're going to get AC out of it, so you don't have to have, since it's AC, you don't have to have a watt. You don't have to have a coupling capacitor. These transistors have to be what we call complementary pairs. They got to be matched. So, of course, we couldn't get much power out of it. So most of your transistors have what they call a complementary pair. So up here, this might be a 3904. Down here, this would be a 2N3906. And the 3904, the 3906 is a complementary pair of 4. Now, what does that mean, a complementary pair? It has the same specs. So if we looked at the specs, as the breakover voltages and the frequency response and everything for 3906, it would be the same as the 3904. Except one of them's a watt. One of them's a NPN and one of them's a watt, PNP. TIP 41 and TIP 42, those are complementary pairs. We wouldn't get very much drive out of I think, 200 milliamps out of a 3904. But you get into some of those big guys, And they parallel them, by the way. We'll show y'all a power amp later on where we can parallel transistors. We just hook them in parallel. I think I got a schematic somewhere I'll show y'all. And we'll have a power amp. We got one in here that's burned up. We never have tried to fix it. I'll go show y'all, let y'all look inside of it. Now, this is a Class AB. But it's still 75, these guys are still 75% efficient, right? Because we're going to have to do some bias on this. One thing, we're going to have to do some type of bias to get rid of what we call the crossover distortion. So they're going to consume a little bit of power, but not very much. Now let's say if I came up here and did this. So Class B is 180 degrees of the input. So they work a lot like a half-wave rectifier, right? Except this guy down here is giving me my negative. This guy over here is giving me my what? My plus. Are we okay? Yes or no? I'm going to put a resistor right here for right now. Let's say I come over here and through another resistor, I connected this to like a minus some voltage. So this is common, this is minus, so right now this transistor is off, right? My input signal comes up. What's it going to have to get to right here before it turns on? About 3.7 volts, right? Right? So my input is changing, and then it drops down. So let's say this goes up to 5 volts. My output, what I would get, and this is a common emitter, so it's going to be out. What we're going to get is we're just going to get a little thing that looks like this. So what's this? Is this going to be 180 degrees? It's going to be less than 180 degrees. This guy right here is basically not conducting current at all, right? You understand that? So it's just there to bias. It's always looking at a reverse bias junction. So the input signal turns it on, but it turns it on for less than 180 degrees. These guys right here are 95% efficient. But what good would they be doing for an amplifier? Not much, right? Unless we put something up there that regenerates the sine. And if you hadn't had AC, don't worry about it. But what we do is we have these circuits that we call tank circuits that basically absorb energy and then they return energy. And they consist of capacitors and inductors. So normally these guys depend on the output to be at the same frequency. And what we do is we replace this resistor right here with a tank circuit. And this circuit would be tuned to this frequency right here. So what would happen is here we would charge the tank up, and then when it dropped, this guy here cut off, it would discharge and generate the cycle. Now, where does these guys come into play? Something that tries to run at the same frequency. They're about 95% efficient. So that means it only takes 5% of my power to run them or less. Where do you think these things come into play? But the frequency has to be constant. The frequency amplifier has to be constant. Where do you think these guys come into play at? Huh? Well, yeah, electronics. They're all electronics filters. Everybody's got one of these, probably wearing it on the side right now or in their pockets. Cell phones. Well, see, cell phones transmit at a carrier. And the carrier is always what? The same frequency. Now we modulate it. So this guy here has a bandwidth. We modulate this. Modulation means we take. So this is transmitters right here. This is RF transmitters right here. They use Class C amplifiers. Because when you transmit RF, you usually transmit it at a frequency, right? You understand that? So your cell phone transmits at a frequency. These guys here are about over 95% efficient because they're off most of the time. They turn on long enough to charge up that tank circuit up there. When they cut off, the tank circuit discharges. Your antenna would probably be coupled right here. This is actually a transformer. This inductor is a transformer. And your antenna would be over here. And there's your. So every radio station I know of uses a Class C to output them. 95% efficient. At least. Because they're off most of the time, right? They only turn on long enough to do what? Charge that tank circuit. And then when they turn off, it discharges back out into the system. So these are RF transmitters there. So I guarantee you, if you got the schematic on your cell phone, what would you see hooked up to the antenna inside there? Class C. Less than 180 degrees. Yeah, the inductor and the capacitor. Let me redraw it. So the resistor's gone. So what turns into the load for the amplifier is a tank circuit. So this would be VCC up here. And then I would have an inductor that's actually a transformer too, serves two functions. And then we'd have a capacitor. So the inductor, the primary, is actually serving as the inductor for the tank circuit, and then your antenna is over here. There's a little transformer in there, high frequency transformer. So these guys are biased off. The input signal turns them on, but it actually has to go in amplitude before it turns on, right? Yeah, class C. Less than 180 degrees. So we have class A is 360 degrees of the input. So no matter what the signal looks like, it's going to be a mirror image. It's going to be an image of that on the output, right? We got a class B, but what's it going to do? It would cut off one side. We don't use that. We use that in saturated switches all the time. That's class B. So when you do a saturated switch, that's class B. But we combine two class Bs, right? You understand, and come up and get what we call a class what? AB. So the output looks like a class A. But what are we doing? We're using two class Bs. Two class Bs do 180 degrees. Actually, it's slightly less, but we'll show y'all later on how we can turn it, how we can bias it so it's perfect. I mean, it's beautiful. You get rid of what they call crossover distortion. And that's it, guys. And we'll look at common collectors just a little bit, and then next class. And I think our next test is next Tuesday. Huh? Okay, what is the third? That's Thursday, right? What's November the 2nd? No, something's coming up on November 2nd. That's nothing to do with y'all. It's something going on with me. Y'all okay on impedance matching? Y'all got a good idea of dB? We talked about a lot tonight. dB is just a way of You what? Well, we bring it up here. I'll show you how to do that. It's real easy. It's got a log. Don't have a log key on there. But you got one of those reverse. You got one where you got to hit that D decimal on there, right? No, you don't. It's got one key on there. It's got called S/D or something like that, or -D. You don't have to hit shift. Yeah. Just hit that one key and it'll switch you between the two. Okay. Questions? Anything I want to go back over real quick? What? What is dB? dB, we use those in power systems all the time. Audio, you're going to run into it all the time. A lot of your ICs talk about dB separation and this kind of stuff. So it's a pretty important concept to understand. So engineering notation deals with what? They're not the same. Don't get them confused. So a lot of people, when we do that, when we do that 3.6 times 10 to the minus third, what people try to use is they try to use that key on their calculator that does that, and that's not the same key. Okay. So that's when we have to use we call it the exponent key, or EXP. And what that stands for is that right there. Some number raised to 10 times some power, right? When we deal with Bell's, we are dealing with this guy right here. 10 raised to some power. Not something times 10 raised to some power. It's 10 raised to the some power. We call this the base. Y'all have had math, right? So when we deal with exponents, we have two things. We have what we call a base, and then we have the exponent. Well, what's a Bell? It's the exponent that 10 would be raised to. So like we said, we can represent any number we can represent 10 raised to some power, whether it's positive or negative. It would be less than 1 if it's a fraction. It would be more than 1 if it's a whole number. So I've got 10 raised to the second power, which would equal to 100. Now what we do to go to dB is we take the Bells and we multiply it by 10. So instead of saying 10 raised to the second power, here I would say 20 dB. Be exactly the same thing. So dB is a form of, like we use milli and micro. It's not a unit. It's not volts. It's not amps. It's just a way we can represent very large and very small numbers, right? So if I had 39.6 dB, the actual number would be 10 raised to 3.96 power. Because why? Because dB is real nice, because all I have to do is just shift the decimal point. Right? You understand that? We shift it to the right when we multiply by 10. We shift it to the left when we divide by 10. So when you hit the log key on your calculator, what does it give you? If you got it set for common log, what does that give you? What does the log key give you? Now, what does it give you if you use the log key? So let's say 100. Hit the log key and see what it comes up with. 2. Well, what is 10 raised to the second power? So what is the log? The log is the exponent that 10 would be raised to come up with that answer. So the log is that number right there. That's all it is. So if I got the log of 1,000, it's going to be 3, right? If I got the log of 10,000, it's going to be 4, right? You understand? If I got the log of 10,178, it's going to be somewhere between 4 and 5, right? Makes sense. So that's all the common log is the Bells. It's the exponent that 10 would be raised to get that number. So if I came up here and said 1,000, and I took the log of 1,000, it's going to say 3. To convert it to dB, I just add a 0 and call it dB. I multiply it by 10. So 30 dB is equal to 1,000. So all you do is take the common log and move the decimal point to the right one spot and round, either to what? 1 or 2 decimal points. Very seldom will you see more than 2. Because as soon as you get past 2, then it's going to get to the point where you just might as well use the actual number, right? So dB is just a way we can round. So what I do if I got a power gain, which is AP, so that's my power gain. Well, what I want to represent that in dB. So what I'm going to do, the first thing I'm going to do is I'm going to take the log of that. Right? Because we're representing the power gain in dB. All we're doing is taking this number and representing it in, we're taking the common log of it. So what power gain do y'all want? Huh? What power gain do you want? Huh? 40. Okay, 40. So how many dB would that be? Well, the first thing I want to do is I'm going to take a log of that number. What do I come up and get? 1.6. Okay, then in my head, I move that to the left. I move it to the right one spot, and I say 16 dB. That's all there is to go into dB. We take the common log of the number, which tells us what the number what exponent we use to get that number, right? You understand? So let's say I wanted to go back, so 16 dB. Now let's say I want to find the actual number. Well, in my head, I'm going to move the decimal point right there, and I'm going to raise 10 to the 1.6 power. So right beside the dB key, or even sometimes the log key, sometimes the power of 10 key is right there by it. On most calculators, it's on this calculator right here, here's log, and what's right next to it? See, some of them it's a shift, sometimes it's the same key, because that's all they are. They're the opposite of each other. But what you got to do to go to dP is just shift it to the right or shift it to the left. So you take dB and shift it to the left to get the veil, or you take the veil and shift it to the right to get the dB. Right? That makes sense. Now the problem we have is that we're concerned with voltage. We're concerned with power gain. But the problem is it's hard to measure power. We don't even have a watt meter around here. I need to ask Nancy to try to get us. But when you measure power, you got to measure two things, right? You got to do what? So my meter would have to measure two things. It would have to measure voltage and current. A voltmeter measures volts. So what we're trying to do is trying to figure out what would be the power relative to what? Voltage. Power varies with the square of the voltage. So instead of multiplying by 10, taking here, so what do we do to go to dB? We take this, and then we multiply by 10. That takes us to dB, but that's power dB. What we're trying to do is figure out power dB relative to voltage. So what I do? Well, I calculate my voltage gain, right? You understand. So let's say we have a voltage gain of 80. But I'm trying to get it relative to power. Power varies with the square of the voltage. So what I would do is I would take my voltage gain, which I say 40, instead of multiplying, I'm going to take the log of that, and instead of multiplying it by 40, I'm going to multiply it by 20, because that's the square, right? You understand? Yes or no? Yeah, we did this a while ago. So I said 10 to the first, right? You understand? Which gives me a watt, which would be 10 dB, right? You understand? It gave me 10. I come over here and said 10 to the second, which would be 20 dB, and it squared it. It came up and squared the voltage, right? You understand? So that's why here we do what? We multiply by 20. We take the voltage gain, we take the log of that, and we multiply it by 20. If I know that, and now this might take a calculator, but most people can divide by 2 in their head, right? So you divide by 2 and shift it over 1. So what do we come up and get? Came up and got what? 32.32 dB. .something. We got to round. Normally we round to 1, 2, no more than 2. So let's round it to 1 decimal. What would it be? The more you round, the less accurate you're going to be, right? But it's what we got. Yeah. So you're taking 3.2 dB. Okay. So it'd be 32 dB. So how would I get that back to this right here? So that means that's 32 dB, right? Okay. Well, let's see how much power gain we would actually have. So my power gain, I would come up here and I would divide that by 10. 3.2. So I take, this would be the actual power gain I got. What would that be? Now this is kind of misleading, but yeah. I know it's going to be about 1,000. It's going to be greater than 1,000. Yeah. What is it? Okay. Something's coming out wrong. You sure this is 32 dB? 32 dB is a lot. I'm going to take 40. I'm going to take the log of that, right? Okay. And I'm going to multiply that times 20. If you come up here. Okay. Then what I'm going to do, something's wrong. So let's say we take this and divide it by 20 and then raise 10 to that power. So if I come over here and have a gain of 40, which is a lot of gain, by the way, then I take the log of that, and then I multiply that times 20. And then I come up here and divide that by 10. That comes up and gives me that, so you're right. So that would be the power gain we had. I didn't round. I used the actual number. You see what I did? I didn't ever change it. So 1600 for the power gain with a gain of what in voltage? 40. So that means if I put 1 volt in, I would get what out? 40 volts out. That looks a little high to me, but that's right. So I did a good job. So what we do is we can get a relationship of the power gain by measuring voltage. So we could calculate that. We could come up here and set up a circuit. And, we're not going to do it. But y'all can probably do this later if you want to. So let's say we got a gain of 40, and let's say I run 1 volt into a 1K ohm resistor, and we calculate the power. So we can do that. So that would be V squared over R, so it'd be 1 squared over 1K, 1,000, and what would be my power? Not very much, right? What we got? 1 milliwatt. So now we're going to get a gain of 40, and then I'm going to run that into a 1K resistor. This is on my output, so that's going to be 40 squared divided by 1,000. Hopefully you get, huh? 1.6 watts. 1.6 watts. What's my gain? 1 milliwatt in, 1.6 watts out. Gain of 1600. So what we did here is, here we actually did power, but we did it relative to what? To voltage. Okay, so what we did over here is we figured this, we came up with 32 dB. To figure out what power that would be, we took 10, we divided this by 10 instead of by 20, right? Because we're dealing with power. And we came up and got 1600. Over here, we actually put that into a circuit where here I had 1 volt at 1K and 40 volts at 1K, because that would be my gain on the output. And it came up to be 1600. Isn't that neat? But we calculated gain relative to what? Voltage. Which is pretty neat. And that's why we do the 20 log, because power varies with the square of the voltage, right? And then we looked and used that to figure out where the 7.7 where the 7.07 came from. Are we okay? So that help you, Dwayne?
Yeah.
That's neat. I mean, so neat. And it when you start using terms like that, people think you're smart, right? You know, you start talking about all this stuff, and of course, I don't talk much about my wife. She wouldn't understand it. I mean, my wife's smart, but she just don't understand electricity or electronics. So, you start talking about dB, and you know, well, I got a 3 dB gain or 30 dB out of that. Everybody be going like this, and they say, "Well, that's so smart." And they have no idea what 30 dB is, but you know it's what? It's 1,000, you know, because you know, powers of 10s are hard because they jump so big. You know, you go from 10 to the second to the 10 to the third, you go from 100 to 1,000, right? So you got, you know, 21 dB, which would be 10 raised to the 2.1, and basically all I can figure out, I'm sure we got some geniuses out there, but I just know it's going to be somewhere between 100 and 1,000, right? Because it jumps so much. So 2.5 would be probably in the center, right? You understand? So we jump 500 just by going from 0.5, because you go one number over here, and over here you go a power of 10. So, but you get a rough idea of, not ever even picking up a calculator. You know, if somebody says 20 dB, you know it would be a gain of 100, right? If they say 20.3 dB, you know it's going to be what? You know it's going to be greater than 100 and less than 1,000. It's probably less than 500. So it's going to be in that range right there, right? You understand? Yeah, so 2.5. See, it don't even vary there. So that's a log. 2.5, which you would think would be 500. If you raise 10 to that power, it's actually less. But if you go to 2.6 and raise it to that, okay. But if you go to 3, now all of a sudden you're up at a what? 1,000. So see, I got it close. I said it. I knew it was over 100 and less than 500. Okay, guys. Let's go.